Hey Goose. So I just saw the YouTube video for the presentation that you practiced. I thought it was pretty good. Of course, I have some things that I think we could fix. So I wrote up a thing in Word that I probably sent to you, and hopefully, and I'm gonna go over it now just because I thought that would be useful. So in the beginning, the first thing you do is you introduce O3. You say O3 is the group of 3 by 3 matrices that are orthogonal. And it just sounds kind of clunky. You could make it sound much more condensed if you just said O3 is the group of 3 by 3 orthogonal matrices, which is what you do for SU2. You say SU2 is the group of 2 by 2 special unitary matrices. So same thing. I think it's good that you prove that O3 is length preserving. Totally do that. Now, after you say that it splits into O3 splits into two subcollections, one with determinant -1 and determinant +1. Then you say determinant +1 is SO3. Right after that, when you start going to SO3, like every time that you practice this, like the first thing that you say is SO3 has a Lie algebra, which is true, but like very out of the blue, and then you don't say anything about Lie algebras for a while, so just don't even say that right away. You want to mention that it's a Lie group, which is what you do. You say it depends continuously on these parameters. That's perfect, right? How you're doing it. So just nix the Lie algebra comment right there. Just a note, you might want to say that you say, an element of SO3 depends on 3 parameters, theta1, theta2, theta3. You might mention that the identity is when theta1, theta2, and theta3 all equal 0. Just a neat fact. Okay. At 9 minutes and 45 seconds, you use the word representation. Someone might say, what's a representation? And the easiest, simplest answer, which you know, Goose, is that it's a map that takes in an element of SO3 and spits out an n by n matrix, where n can be anything. Take in an element of your group, spit out a matrix. That's all a representation is. Okay, and now 11:13. You start talking about quantum mechanics. That when we're talking about expectation values, if you multiply the state by e to the I theta, you get the same expectation value. One comment before is you sometimes use psi and you sometimes use psi in a ket. Just use the ket. You use the ket psi because that's very common notation. And then you say that all the e to the I theta times psi get mapped to some psi. They get mapped to the same psi. Some psi sounds ambiguous. Okay, then you do a really, really good job, Goose, of going over, it's a projective space, so we need to use projective representation. Here's the definition of a projective representation. Phase factor sucks. Before that, you introduced the idea of a universal covering group, and you said that, the representations of the covering group are the same as the projective representations of the group that it covers. You do all of that in a recap all at once, and it makes it into like a paragraph-long sentence, which sounds really cool, and I know because you're combining so many different facts all together, but it makes it hard to understand. So I think just go with what you've said and keep going rather than start all the way from the beginning and rush through to recap. So, okay, now you start to talk about SU2. Did fine. You say that SU2 acts on vectors x, where x is in C2, and then you call C2 the complex plane, but the complex plane is C1. A vector in C1 looks like x plus iy. A vector in C2 looks like a column vector x plus iy, x prime plus iy prime. There's 2 of those. So if you wanted to say something, you could be like it's 2 complex planes, but I would just leave it at C2. And I know, Goose, I'm being picky at a lot of points. That's because like I like to be really technical, and I think you want to impress people, you want to impress your professor, so I think it's good to be technical. 1435, the thing about quantum mechanics, we talked about it a little bit more. I wrote a little thingy in LaTeX. You just want to say that in quantum mechanics, lengths are also interpreted as probabilities, and here's how. We start with a state psi, and the probability to end up in a state phi is the inner product squared. And if I apply a unitary transformation to all the states, such that psi goes to u psi, and phi, the bra phi goes to bra phi times u dagger, then the probability to go between those two states, the u dagger u just becomes 1, and you get the same probability. So it conserves probabilities. And I wrote your thing in LaTeX that will probably make much more sense than what I just said. Okay, then you introduce the SUN structure, and for n equals 3, you get 3 parameters, and then you go off on a cool tangent about the weak force. But these parameters correspond to the W plus W minus and Z. You say these parameters are the W plus W minus and Z, but it's not an equal sign. It's a correspondence, like an arrow, if that makes sense. Okay, 18 minutes. After you've talked about SU2, you talk about SU2's Lie algebra. Did a cool job with that. It's the tangent plane at the identity. Why don't you go right ahead here and introduce J1, J2, J3? Write them out. Say these are the basis vectors for the Lie algebra, for the tangent plane at the identity. They're also called generators. Write them in explicit matrix form. I told you what they are. And then introduce the commutation relation right then. It's a perfect opportunity. It flows really well. Because they come up later, but they're never explicitly said what they are. And you perfect job saying that any b in SU2 can be written as e to the I theta times j. You did a good job with that, showing how infinitesimal transformations exponentiate to finite transformations. Okay, and now you start with Euler angles. And Goose, you did a fine job with this. There are just some things you need to polish up. So when you did the first two sections on O3 and first three on O3, SO3, and SU2, you do a really good job at introducing them. You're like, now we're going to talk about SU2. Whereas here, you don't do that. You don't say, now we're going to talk about Euler angles. You just kind of go through, and it's not clear that we're doing a new topic. So you might want to say, now we're going to discuss Euler angles. And maybe, like you said you like to know the motivation of something before you go into it because it helps you remember it more. The motivation behind Euler angles is they give you an explicit way to write any element of SU2. And that's as e to the I alpha J3, e to the I beta J2, e to the I gamma J3. I think you forgot the i's in the exponents in your presentation, so watch out for those. You wrote down the commutation relation for the j's here. You forgot the I. It's commutator of J1, commutator of Ji and Jj is I epsilon I Jk Jk. You just said it was epsilon I Jk Jk. Something to watch out for. Watch those i's. You now know that the gamma angle is the one that comes first because that product of exponentials acts on something to the right. Okay, and then you want to start talking about at the final thing you talk about with the, combining those exponential factors. The way you might want to say that is, since these j's don't commute and we can't add the exponents, how do we really know that this product of exponentials is really in SU2? Because that's what we want to know. We want to know that that product is still in SU2. Um, Baker Campbell House store formula. Um, and I told you how to spell Campbell right in the in the document. Um, you all of a sudden start talking about SO3 again. You're talking about SU2, so keep it in SU2 unless you're going to provide the connection with representations. We said that there's a map that takes the J's, which are the generators of SU2, to the J primes, which are the generators of SO3. There's a representation that takes you from one to the other. We talked about that in my office, and you wrote it down inside that red box. So keep it with SU2, unless you're going to talk about that. And you wrote down the formula. It's an infinite sum of nested commutators. And now, like, the reason why we know that this works is because, and you started it well, each of those commutators is still in the Lie algebra of SU2. Those generators, those J's, are not in SU2. They're in the Lie algebra of SU2. So each one of the commutators is still in the Lie algebra. And so that infinite sum of commutators will still be in the Lie algebra, because it's just a sum of Lie algebra elements is still a Lie algebra element. Then we know that when you exponentiate a Lie algebra element, you get an element of the group. So that product of exponentials will still give you an element of SU2. And then you're done, finito, take a bow, receive roses and applause, and you can drop the mic and walk out. All right. I hope that helps, Goose. Like I said, lots of picky stuff. You might not want to implement all of it because it's a lot to fix, or not a lot to fix. Sorry. It's a lot of nitpicky things that might be difficult to implement like right away with a couple hours to spare. I don't know when you're going to be watching this. But I think you're going to do really good, Goose. I would say you did like 95% a really good job. It's just technical things. I think you're going to do really well. I think he's going to be impressed. I think other students are going to be impressed. And I'm rooting for you, Goose. All right, good luck. I love you.